Welcome to the Deep Dive. Today we're kicking off a really fascinating journey. We're going to be tracing the incredible westward path and, frankly, the huge impact of mathematical and astronomical ideas that started in India.
That's right. Particularly ideas linked to the Aryabhatan tradition.
Yeah, exactly. We're talking about some really fundamental concepts here.
We really are. Things like the decimal system. I mean, the way we actually write numbers today. And the whole idea of zero, which was just groundbreaking.
Groundbreaking is the word. Plus sign-based trigonometry and some, well, really clever computational methods.
And exploring how these traveled across continents, it really tells a compelling story about how connected intellectual history has always been. It's not these isolated pockets we sometimes imagine.
Absolutely. You think of science progressing neatly in one place, but the reality is this amazing network. Thinkers building on insights from, all over the world.
Yeah, a real exchange.
So our mission, if you like, for this deep dive is to figure out how these foundational concepts, this ancient code, how it traveled west, how it landed and was adapted in the Islamic world.
And then how it eventually reshaped science in Europe. It's like unlocking a kind of secret history of how we got to where we are now, scientifically speaking.
A secret history. I like that.
Mm-hmm.
Okay, so these ideas are like seeds, right? Carried on the currents of trade, maybe diplomacy.
Exactly. And of course, scholars traveling, searching for knowledge, that was huge. These seeds found fertile ground in new places and, well, they blossomed, sometimes in surprising ways.
Okay, so let's unpack that early stage. This spread from India. It wasn't like flicking a switch, was it? It sounds more like a slow burn.
Precisely. India developed these really sophisticated ways to calculate, solving practical problems, theoretical ones too. And naturally, that got the attention of other cultures they were trading with or had diplomatic ties with.
Makes sense. If someone has a better way to, say, calculate cargo or navigate,
you're going to be interested. And scholars moving around, eager to learn and share, that was crucial for this early sort of diffusion.
Right. And then there's this moment, you mentioned the 8th century, around 770 CE. Indian scholars arriving in Baghdad. That sounds pretty significant.
Oh, it was a watershed moment, definitely. The records show that during Caliph al-Mansur's reign in Baghdad, which was a real intellectual hub, this delegation from India arrived.
And they brought texts with them. Astronomical texts.
Yes, important astronomical texts and tables. And crucially, these were then translated into Arabic. They became known collectively as the Sindhind.
The Sindhind. Okay, that name alone sounds like a clue, doesn't it?
It absolutely does. Sindhind is basically the Arabic version of the Sanskrit word siddhanta.
Which means?
Broadly, it means like an established system or doctrine in astronomy or mathematics. So that linguistic link is a dead giveaway for the Indian roots of the knowledge in these texts.
Okay, so were these direct translations of Aryabhata's own work? Or were they based on later Indian stuff?
That's still debated a bit among scholars, the exact source texts. But the general thinking is they probably drew on later siddhantas, maybe Brahmagupta's Brahmasui Siddhanta.
Okay.
But here's the fascinating part. Even if they weren't directly Aryabhata's words, these texts still contained the core elements, the really fundamental stuff that trace right back to his innovations.
Like the big ones we mentioned at the start, the decimal system, trigonometry.
Exactly. The most important ones were, first, the fully developed Indian positional decimal system, using 10 digits, 0 through 9, and the place value idea, the system we all use.
Hard to imagine life without it now.
Totally. And second, a really sophisticated system of sign-based trigonometry. These were like mathematical power tools compared to what was common elsewhere then. Way more efficient, way more accurate.
Especially that place value system with 0. Being able to represent nothing and use it in calculations, that must have been game-changing.
Absolutely game-changing. Think about trying to multiply large numbers using, say, Roman numerals or Greek letter numerals. It's incredibly cumbersome. This Indian system with 0 made complex calculations so much easier.
So these Indian ideas land in Baghdad, this buzzing intellectual center. How do they start to, catch on and really get woven into the thinking there?
Right. Well, that brings us neatly to our next really key figure. Muhammad ibn Musa al-Khwārizmī.
Al-Khwārizmī. Okay, that name definitely rings a bell. A Persian scholar in Baghdad, early 9th century.
That's the one, an absolutely brilliant mind. And he was just crucial in formalizing these Indian concepts and getting them out to a wider audience, not just in the Islamic world, but eventually beyond.
So he was like a conduit Or maybe an amplifier?
Both, really. His impact was just enormous. He wrote this really important book focusing specifically on Indian calculation methods.
Okay.
And this book, when it was later translated into Latin, it became known as Algoritmi de numero Indorum, something like Al-Khwārizmī on the Hindu art of reckoning. And this book was just a clear, systematic guide to the Indian positional decimal system, basically a user manual for this revolutionary way of doing math.
Wow. And this is how the digits 1 to 9 and, crucially, 0 really entered the Arabic-speaking world, pushing out older methods.
Precisely. He explained how to use the digits, how place value worked, and the role of zero afra in Arabic, which came from the Sanskrit śūnya, meaning empty or void.
Oof. Sounds a bit like cipher or zero.
Exactly. That's where those words ultimately come from. Al-Khwārizmī meticulously showed how powerful and efficient this system was. Calculations that were just horribly complicated before became straightforward.
It's just mind-boggling, the impact of that one work.
Yeah.
And his name. It ended up giving us a fundamental term in computing, didn't it?
It did indeed. The Latin version of his name, Algoritmi, is the direct origin of our word algorithm.
No way.
Yes. It just highlights how central he was in laying out these step-by-step procedures for calculation procedures that were fundamentally rooted in those Indian methods he described.
So every time we talk about an algorithm, we're unknowingly nodding back to the Al-Khwārizmī and through him to ancient India.
Pretty much, yeah. It's an amazing historical echo.
That is incredible. Now, Al-Khwārizmī didn't just stop at arithmetic, did he? There was another famous book.
That's right. Al-Kitab al-Mukhtar Fusab al-Jayb wal-Muqabala.
Okay, say that again slowly.
Al-Kitab al-Mukhtar Fusab al-Jabr wal-Muqabala. Roughly, the compendious book on calculation by completion and balancing.
And al-Jabr. That sounds familiar too.
It should. That word, al-Jabr, referring to one of the basic operations for solving equations, he described the process of restoring or completing. That's where we get our word algebra.
Wow. So algorithm and algebra. This guy was seriously influential.
Hugely. Now, algebra itself has a complex history, many contributors, potential influences from different places, maybe even earlier Indian problem-solving ideas. But Al-Khwārizmī's book was foundational in giving it a systematic structure and, well, its name.
So his influence spread from basic numbers to this more abstract realm of algebra. What about astronomy? Did the Indian ideas filter through there too via his work?
They certainly did. He compiled astronomical tables known as Zish, which became very widely used. And crucially, these tables incorporated sine values.
Sine values derived from the Indian concept.
Directly derived from the Indian concept of G.
Jayb. Okay, that seems like a really key term here. What exactly is G, and how did it morph into the sign we learn about in school?
Right. J is Sanskrit. In Indian trigonometry, it essentially refers to the half-chord of an arc in a circle. It's related to what we now call the sine function, but specifically calculated for the half angle.
Okay, half-chord.
When this concept and the tables of values were adopted into Arabic, the term G became jayb. Now, here's a fascinating linguistic quirk. Jayb in Arabic can mean chord or sign in this mathematical context, but it also means bosom or pocket or opening in everyday language.
Uh-oh. I can see where this might be going.
Exactly. When these Arabic texts were translated into Latin, probably in the 12th century by Gerard of Cremona, he encountered jayb. Maybe he misunderstood the geometric meaning, or maybe he saw the curve and made a metaphorical link.
He translated it using the everyday meaning.
He rendered jayb as sinus, the Latin word for bay, curve, fold, or even bosom.
So our mathematical term sine comes from a possible mistranslation, or at least a very literal translation, of an Arabic word that itself was derived from a Sanskrit term for a half-chord.
That's the story. It's an amazing example of how ideas and even names can get transformed as they travel across languages and cultures.
Incredible. And did other Islamic scholars build on this?
Oh, yes. After Al-Khwārizmī, you had figures like Al-Bīrūnī, another brilliant astronomer. He significantly refined the sine tables, made them more accurate, and he also helped develop other trig functions like tangent and cotangent, building on that same Indian foundation.
So the whole toolkit of trigonometry we use today.
Its roots go straight back to Indian insights, passed on and significantly enhanced by Islamic scholars. It's fundamental for navigation, surveying, physics, engineering, all resting on this inherited knowledge.
It really shows the debt modern science owes to these earlier traditions. Okay, let's shift focus slightly. There's another major figure who engaged directly with Indian science, Al-Bīrūnī.
Ah yes, Abu Rayyan al-Bīrūnī lived a bit later, around the turn of the 11th century. A true polymath, incredibly learned, and he had a very direct connection to India.
Right, he actually traveled there and spent time there, didn't he?
He did. Around 1030 CE, he spent a considerable period in India. He wasn't just a tourist, he immersed himself in the culture, learned languages, studied the philosophy, and crucially for us, the scientific traditions.
And he wrote about it.
Extensively. His major work, Kitab al-Hind, or an inquiry into India, is just this incredibly rich, detailed account of Indian life and thought at the time. It's an invaluable historical source.
So what did he have to say about Indian astronomy and mathematics? Did he encounter the Aryabhatan ideas?
Oh, definitely. He meticulously documented different schools of Indian astronomy, and he certainly discussed Aryabhata's teachings in detail. He accurately described Aryabhata's astronomical measurements and parameters.
And even the idea of the Earth spinning.
Yes, even the theory of the Earth's rotation on its axis. Al-Bīrūnī clearly understood that this was a significant idea attributed to Aryabhata, and he laid out the arguments for it. He recognized Aryabhata as a major figure.
That's fascinating. How did Al-Bīrūnī himself react to that idea, a rotating Earth, coming from the dominant Greek tradition of a stationary Earth?
Well, that's such an interesting part. While he presented Aryabhata's arguments fairly and acknowledged their logical points, Al-Bīrūnī ultimately rejected the idea of Earth's rotation, mostly because it clashed with the prevailing physics of his time, which was heavily based on Aristotle and Ptolemy, the geocentric model. A stationary Earth was central to that whole picture.
So the established scientific consensus, basically.
Pretty much. He also raised what seemed like common sense physical objections back then. Like, if the Earth is spinning so fast, why don't we feel it? Why aren't birds left behind in the air? Why aren't things flung off the surface?
Right, the lack of obvious physical evidence as they saw it then.
Exactly. These objections seemed insurmountable based on the physics they understood. So even though he documented Aryabhata's view accurately,
he stuck with the geocentric model.
He did. But, and this is really important, by carefully documenting these Indian ideas, even the ones he disagreed with, Al-Bīrūnī ensured they were preserved and transmitted. His inquiry into India became a key source for later scholars in the Islamic world, and eventually, knowledge from it filtered towards Europe too.
So he acted as a vital, critical bridge. Even if he didn't personally accept Earth's rotation, his work kept the idea in circulation and documented its Indian origins.
Precisely. His meticulous scholarship was incredibly valuable for preserving and sharing this knowledge, making him a crucial link in the chain, even as a critical observer rather than just a promoter like Al-Khwārizmī perhaps was for the numerals.
Okay, so the knowledge is circulating widely in the Islamic world. Let's follow the trail westward again, towards Europe. It seems like the transfer to Europe was maybe slower, more indirect.
That's generally right, yes. It wasn't as sudden or direct as the initial influx into Baghdad. The main pathway into Europe was through translations, mostly from Arabic into Latin.
When did this start happening in a big way?
Primarily in the 12th and 13th centuries, European scholars, particularly in places like Spain and Sicily where cultures mixed, started actively seeking out and translating Arabic works on science, mathematics, philosophy.
And hidden within those Arabic texts were the gems of Indian math and astronomy, often refined by Islamic scholars.
Exactly. They were discovering this wealth of knowledge that had been developed and preserved in the Islamic world, including the crucial Indian contributions.
And who was a key player in actually getting these ideas, especially the number system, adopted in Europe?
Well, the name that stands out most prominently here is Leonardo of Pisa. We know him better as Fibonacci.
Fibonacci, of the sequence fame.
The very same. Though his popularization of the Indian numeral system was arguably even more impactful in the long run, he lived in the early 13th century.
And how did he encounter these ideas?
He traveled really widely as a merchant's son, all around the Mediterranean, North Africa, the Byzantine Empire, Sicily. He learned directly from Arab mathematicians and merchants.
And he saw the advantage of their number system.
Oh, immediately.
Yeah.
He saw how much better the Indian system, what he called modus Indorum, the method of the Indians, was compared to the clunky Roman numerals still used in Europe.
Roman numerals.
Oh, yeah.
Yeah, trying to do business or complex math with those must have been tough. No zero, no place value.
Incredibly limiting. Fibonacci recognized the sheer elegance and practical power of the 9 digits plus 0 and the place value concept. It was just a vastly superior tool for calculation, a real paradigm shift.
And he didn't just keep it to himself. He actively tried to spread the word.
He did. His famous book from 1202, Liber Abaci, which translates as Book of Calculation or Book of the Abacus, though it was really about calculation without a physical abacus, using the new numerals, this book was absolutely key.
What was in it?
It wasn't just theory, it was a really practical guide, full of examples showing how to use the Indian numerals for everything from basic addition, subtraction, multiplication, division,
To more complex things.
yes, things vital for merchants and bankers. Currency conversions, calculating interest, profit margins, bookkeeping. He showed how this system made business math so much easier and more accurate.
So he aimed it squarely at the practical needs of the time. That sounds smart.
Very smart. And that practicality was probably the key to its eventual success. It wasn't just an intellectual curiosity, it offered a real competitive advantage in trade and finance.
Was it adopted quickly? Or was there resistance to ditching Roman numerals?
There was definitely resistance. People are often slow to adopt new ways, especially something as fundamental as numbers. Some found it unfamiliar, maybe even distrusted it initially, but
The efficiency won out.
eventually, yes. The sheer usefulness of the Indian system couldn't be denied. It gradually spread across Europe over the next few centuries. This numerical revolution, sparked by Fibonacci's advocacy, laid an absolutely essential foundation for everything that followed scientifically.
Like the scientific revolution later on.
Absolutely. Think about Kepler's calculations of planetary orbits or Newton's development of calculus. Could you even imagine doing that kind of math with Roman numerals?
Honestly, no. It's almost unthinkable. The Indian system was a necessary prerequisite.
It really was. A fundamental tool had arrived.
Okay, so the number system makes its way, eventually triumphs due to practicality. What about trigonometry? We know the word sine came through Latin via Arabic.
Right, sinus. That concept and the name definitely arrived through those 12th century translations we mentioned. So Europe got the basic function.
But was it the full package? Did the advanced Indian methods for calculating sine values or the later stuff from the Kerala school also make it across at that time?
Not really, no. That seems to have been a more complex and less direct story. The sophisticated computational techniques like Aryabhata's method using finite differences to build sine tables, or the amazing infinite series for trig functions developed in Kerala centuries later, those didn't seem to transfer directly or completely in that initial wave.
So Europe got the sine function, but not necessarily the advanced how from India or the Islamic world, at least not initially.
That seems to be largely the case, yeah. European mathematicians, particularly during the Renaissance, kind of had to rebuild or rediscover much of trigonometry for themselves.
How did they do that?
They often went back to the Greek geometric tradition, studying Euclid and Ptolemy. Ptolemy's work involved calculations with chords of circles, which are related to sines. Figures like Regiomontanus in the 15th century did a lot of work reconstructing trigonometry based on these classical geometric methods.
So it was less about directly adopting the Indian Islamic computational methods and more about rebuilding from Greek foundations, but eventually incorporating the sine concept that had come through Arabic.
Kind of a parallel development that eventually converged. They developed their own ways to calculate sine tables, often using geometry, and later, with the development of calculus, new analytical methods emerged. The sine function itself, derived ultimately from India via the Arabic jayb becoming Latin sinus, was integrated into this evolving European mathematical framework.
So the journey of trigonometry was more tangled than the numerals.
Definitely more tangled. The name and basic concept traveled, but the sophisticated computational engines behind it in India and the Islamic world didn't seem to make the same direct journey early on. It shows how knowledge transmission can be selective and complex. Different pieces travel at different speeds through different routes.
This whole story, though, from India through the Islamic world's golden age to laying foundations in Europe, it just hammers home how global intellectual history really is. It's not separate silos.
Not at all. It's a continuous flow, a conversation across centuries and cultures. Ideas born in one place are picked up, refined, added to, and passed on. What started as these brilliant insights in India's zero, the decimal system, sine-based trig,
Were embraced and significantly advanced by scholars like Al-Khwārizmī and Al-Bīrūnī.
exactly. And then these developments provided absolutely crucial foundational tools and concepts for the scientific leaps that happened later in Europe. It really paved the way for the scientific revolution and, the modern world.
So when we use our decimal numbers or calculate with sine waves, or even run an algorithm on a computer.
We're tapping into this incredibly long and interconnected history, this ancient code, as we called it, originating in India, nurtured in the Islamic world, and eventually becoming part of the universal language of science and mathematics.
It's a powerful reminder of that shared heritage, and maybe a bit humbling too.
It really is, and it definitely leaves us with something to think about, doesn't it? For you, listening, how does understanding this complex cross-cultural journey challenge the simpler, maybe more Eurocentric stories we sometimes tell about scientific progress?
Yeah, what does recognizing these deep connections mean for how we view innovation or the development of knowledge, even today in our own interconnected world?
That's the question to ponder.
A really important one. Well, thank you for joining us on this deep dive. It's been fascinating tracing this remarkable journey across the globe.
A story that really does enrich our understanding of how knowledge grows and shapes our world.